Okay. So today we have Roman Riza, and he will talk about quasi-hermitian random matrix models. So go ahead, Roman.
Thanks a lot for the introduction. I'm going to talk about the joint work with Joshua Feinberg. So the outline of my talk is the following. In the introduction, I will define what I mean with strictly quasi-hermitian and pseudo-hermitian random matrices. I will also tell you some basics. And then I will start with the model of strictly quasi-hermitian random matrices. Since this model already has been mentioned in quite some detail by Joshua in his talk in this seminar last year, I will only briefly mention this case where I will show a motivation, a physical example where strictly quasi-hermitian matrices appear. Then I will come to the main part of my talk, which is when the metric becomes indefinite, and I will talk about pseudo-hermitian random matrices. So in Joshua's talk at the very end, he has briefly shown you some graphics for the case when the metric is diagonal and minus ones. I will show you these results in more detail, and I will also discuss the methods which we have used to get an explicit analytic result. And then in the last part of my talk, I'm going to generalize this, this metric to have t's instead of minus ones. And there we will see that this new model, which will be completely new result, has many different phase transition, both in the cases of complex eigenvalues and real eigenvalues. And I will show you a video where t runs changes with the time. Let's start with the definition of strictly quasi-hermicity. So let B and phi be n times n matrices, where phi just have complex entries, and B is a Hermitian positive metric. Then we will call phi to be strictly quasi-Hermitian with respect to the metric B if it fulfills this intertwining relation. So this simply means that phi is Hermitian with respect to the metric B. For B equal 1, it reduces to the ordinary hermiticity. The general solution of the intertwining relation is given by phi equal to A times B, where A is an arbitrary Hermitian matrix. This result can be found in some papers from some years ago. Thus, given a B, there are n squared independent quasi-Hermitian matrices. Important is that for positive metric, the spectrum of phi is always real. The easiest way to see this is when we write phi in this form here. Then you can see that phi is similar to a Hermitian matrix, provided that the square root of B is Hermitian, which is the case when B is positive. So now I want to relax the condition that the metric has to be positive. I will use the definition which you can find in a paper by Andreas Fring, and we will call it pseudo-hermiticity when the metric becomes indefinite. So the general solution for the intertwining relation still holds in this case, but the spectrum no longer has to be real. It can contain complex eigenvalues which will appear in pairs of complex conjugated eigenvalues. So let me motivate quasi-Hermitian matrices by a simple physical example. Think of a mechanical system with n degrees of freedom. which executes small oscillation around a stable equilibrium. So the equation of motion is given here. The matrix M here is the mass matrix, which is Hermitian and strictly positive definite, and K is the matrix of spring constant, which is Hermitian and positive definite. X is the deviation from the equilibrium point. So, for example, you can think about a system where every mass is connected by a spring to any other mass. We all know how we can solve this problem in terms of harmonic eigenmodes. And the eigenmode equation reads like this here. We also know that for small oscillation around a stable minimum, the frequency must be real. The eigenmode equation we can also write in this form here, where phi is given by the inverse of m times k. Since m and k in general do not commute, it is clearly that phi is not a Hermitian matrix, but it fulfills the intertwining relation. So we have found an example where a quasi-Hermitian matrix appears. For large mechanical systems with high connectivity, this problem naturally lends itself to analyze in terms of random matrices. Then we have to draw M and K from uncorrelated probability distributions. In some paper where we recently have published a preprint, we have taken K from the Wishart ensemble and M we have taken from the shifted Wishart ensemble, as you can see here. C and C tilde are random matrices from this probability distribution here. Then we have used free probability theory, and then we could calculate the density of eigenvalues for the matrix phi given by M inverse times K. Since Joshua has talked about this model in great detail, and also because you find the results in the preprint, I will not go to discuss this model any further. So what I want to do next, I want to ask the question what's happening when the metric becomes indefinite. So in terms of the model with the springs, you can think about some springs lose their inelasticity, their elasticity. There are also other motivations for the indefinite metric. For example, in quantum mechanical system with broken PT symmetry. So now, and in the rest of my talk, I'm going to consider the pseudo-Hermitian case. I will recall you that also in this case, the solution of the intertwining relation is always given by phi equals A times B. In the model, which I'm going to consider in the following, B is a deterministic metric, while A is a random matrix. Since A has to be an arbitrary Hermitian matrix, it is very natural to draw A from the GUE ensemble. So that means we put on the random matrix A this probability distribution here. So this probability distribution on the random matrix A induces a probability distribution on the matrix phi, which you can see here. And the goal is now to compute the statistics of the eigenvalue density of the matrix phi. The average density of the pseudo-Hermitian matrix phi we can obtain from the Green's function, which we get from the resolvent of phi. Here, these brackets denote averaging over the GUI ensemble. We will see that in the large n limit, we can obtain G of W in an explicit closed form. So let me sketch the methods which we have used to find an explicit result. So the first trick is due to Burda, Yannick, and Novak. So the averaging over A becomes easier if one can avoid the product of matrices AB. So for this, we introduce a 2n by 2n matrix H of this form here, which is the resolvent with the resolvent given here. A useful fact, which we will see later, is that the random matrix A here in this block is decoupled from the deterministic block B. In the resolvent, we can see that from this upper left block here, we can get the desired Green's function when we divide here by Z and substitute Z squared by W. What is important to note is that the matrix H in our case is not Hermitian. So for this reason, it can have complex eigenvalues, and its associated Green's function G tilde will not be a holomorphic function. So it is not only a function of Z, but also a function of Z star. Let me explain you this at a simple example. So in the Ginibri ensemble, when n goes to infinity, the density of eigenvalues will uniformly fill the unit disk. The Green's function then is given by G of Z equals Z star inside of the disk, which is clearly not holomorphic. While outside of the disk, the Green's function is 1 over Z. The density the density of eigenvalues we can get by the anti-holomorphic derivative of G. Let's go back to our problem. So as I mentioned, H is not Hermitian, and because of this, G tilde is not holomorphic function. To overcome this problem, we are using the method of hermitization, which you can find in these papers here. For this, we are going to double the matrix again. So we will end up with a 4n by 4n block matrix G hat. So as it is shown here. So each entry in this matrix here is an n times n matrix. And this is the resolvent of this matrix here. Important is now that this matrix, as you can see, is Hermitian. So that means that the G hat is holomorphic function when the complex spectral parameter eta is away from the real axis. So this will allow us to make a series expansion in 1 over eta. And we are going to do this in a diagrammatic way. So the Feynman diagrams which we will use will be Feynman diagrams which have such double lines here, as you can see here. So each of these two lines comes from the two indices in the matrix. So when we use such diagrams to triangulate a manifold, then this direction of these lines give an orientation. And the genus of the manifold will is given by the Euler characteristic. So we will be interested in a limit when n goes to infinity, and it turns out that then the so-called planar diagrams, which are the diagrams which you can draw on a sphere, will give the leading contribution in the 1/n expansion. So higher genus will give 1/n corrections. So the expansion in planar Feynman diagrams will now be the following. We will expand the resolvent G hat in powers of Baire propagators. And then we will rearrange the perturbative expansion in terms of the self-energy sigma hat, as you can see here. So the reason that we are allowed to do this is because G hat is holomorphic. So for this reason, this Born series here will be convergent. So before the step of hermitization, we would not have been allowed to make this rearrangement. Sigma hat, the self-energy, is the sum over all one quark irreducible diagram. We can express sigma hat in terms of the connected cumulants of the distribution of A and the full propagator G hat. Since A is from the GUE ensemble, there is only one connected cumulant. In the planar limit, we will arrive at the following expression for the self-energy, the so-called gap equation. The entries in this matrix here is given by these block traces here. So for example, the 4,4 bar here is the trace of G hat 4,4 averaged over the GUE and then divided by n. So these here are the entries here are just numbers, and we have here a 4x4 matrix. And you can see a lot of entries are just 0. This comes from the fact, which I have mentioned previously, that the random part of the blocks is decoupled by the deterministic part. So we are left to determine these 4 quantities here. After we have taken the complex spectral parameter eta to 0, the block traces are uniquely determined by a self-consistent equation, the Schwinger-Dyson equation. And all our blocks of G hat can be found in terms of these 4 quantities. So in particular, the G31 block, we will find expression which I have given here. It admits 2 different kinds of solution for the Green's function, a holomorphic solution and a non-holomorphic solution. First, I want to discuss the holomorphic solution. From this solution, we can obtain the eigenvalue density on the real axis. So if the 1,1 block trace and the 4,4 equals to 0, then the 4,1 block is a holomorphic function of W, as well as the Green's function G of W, which we can, for which we can find this expression here. It can have these continuities across the real axis, which accounts for density on the real axis. So now it is time to specify the metric. So for simplicity, we will choose a diagonal metric which has k entries 1 and n minus k entries -1. For this specific metric, the holomorphic gap equation reduces to this cubic equation. Lambda here denotes the ratio of k's which are in the matrix. So lambda equals to k divided by n. When we take the right solution for this cubic, then and substitute it into the Green's function, then we can find from the discontinuity in the imaginary part explicit expression for the density. So this here we have found after some cumbersome calculation. So this line density here is supported on the interval from -a to a, where a is given by this long expression here. The delta here is coming from the discriminant of the cubic equation. Instead of looking too long at this complicated expression, I want to show you some plots. So here on the left-hand side, you can see histograms, which shows the real eigenvalue density from a single sample using a numerical simulation with large n. N was about 32,000. So the reason that a single sample is suitable to show the average density comes from the self-averaging effect, which is very typical for the eigenvalue density in large random matrices. So the black lines here are the theoretical prediction given by our formula. And you can see that they match very well with the histograms. So the purple histogram here is for the value of lambda when we are close to a half. And then when lambda decreases, the eigenvalue density is increasing until lambda is reaching towards 0 when it gets the semicircle law, which is not very surprising, as for lambda equals 0, the matrix phi is just the matrix A, which we have drawn from GUE. All of these curves here are normalized in such a way that the total density of real eigenvalues plus the total density of complex eigenvalues are equal to 1. So that means the area below these curves here are given the fraction of real eigenvalues. So when we integrate this formula here, we arrive at the fraction of real eigenvalues as a function of lambda, which I show on the right-hand side in the plot. So this solid black line, this V-shaped graph here, this is coming from the theoretical prediction, while the red and blue dots are coming from numerical simulation with 128 and n equal 1024, averaged over many samples. What you can see is that when we are away from lambda equal a half, the convergence to the theoretical line is exponentially fast, while around this region here, which I have magnified here, you can see that the finite n solution has some deviation from the theoretical one. We also this V-shaped graph also gives a lower bound for the fraction of real eigenvalues, which holds even for finite n and per each sample. This comes from an old result by Carlson. He shows this by a purely algebraic proof. So now I want to come to the non-holomorphic solution. So if the 1,1 trace block and the 4,4 is not equal to 0, all quantities are non-holomorphic function. And this accounts for the eigenvalues in the complex plane, the complex eigenvalues. The boundary of this two-dimensional domain we can find by setting the 1, 1 and the 4, 4 block to 0 in the non-holomorphic gap equation. For any positive metric B, we can show that only the holomorphic solution exists. So this is consistent with what I have said in the beginning, that when the matrix B is positive, that there are only real eigenvalues. On the other hand, when the matrix becomes indefinite, then, so for example, for our choice with the 1 and the -1, then the holomorphic and the non-holomorphic solution coexists. So here you can see an example where lambda is equal to 1/4. So you can see here we have some real eigenvalues, and there is there are 2 domains of complex eigenvalues. The parametrization of this boundary in the large n limit is given as stated here. You can see that these blobs are symmetrically regarding the real line, and this holds for each sample. This comes from the fact that the characteristic polynomial has real coefficients, and for this reason the complex eigenvalues appears in complex conjugated pairs. This is a manifestation of PT symmetry. There is also a symmetry regarding the imaginary axis, but only after averaging over all samples. Let me show you some more graphics. So the blue dots are coming from a scatter plot obtained from a single sample with large n equal around 32,000. I show various lambda, where lambda is a half here. So this is the degenerated case where the theoretical prediction does not show any real eigenvalues. And then lambda is decreasing in this order here. So when lambda is not a half, you can see that there are also some real eigenvalues, and they are very dense here on. So the blue dots form a line. When we are approaching the lambda equal a half, so these two, the upper and the lower blobs, will form into a semi-disk and will merge at the real axis. We can also calculate the area of the 2 blobs by this simple integral here. And when lambda is not bigger than a half, then the result for the area is 2 pi lambda divided by m squared. For the density inside the blob, we will find by Gauss' law that it is a constant, which is equal to m squared divided by pi. So the product of area times the density gives 2 lambda, and they are count for the fraction of complex eigenvalues. And this result is consistent with what we have found on the real axis. Let me also show you some 2-dimensional histograms. Here, these histograms have been obtained by 500,000 of samples with n equal 128, while lambda has been the same as in the previous scatter plots. Indeed, you can see that the density inside in the bulk is quite flat. So it only deviates from the theoretical prediction. You can only see the deviation at the boundary, which is a typical finite n size effect in random matrices, and you can see a similar deviation in the, for example, in the Ginevra ensemble. In the last part of my talk, I'm going to generalize the metric to have this form here. So I have k times the 1 and n minus k, the parameter t. The motivation to study this model, this generalization, is that we can study what is happening when t becomes 0. That means when the metric becomes singular. But this is still work in progress, so I'm not going to talk about this case today. So today I will assume that t is always smaller than 0. So the ratio of the ones we will still denote by lambda. We will now see that there are different phases, both for the real eigenvalues and also in the complex domain. I will now going to show you some animation where t runs over the time. So here you see a frame taken from the video I'm going to show you right now. So you see the blue dots are again from a scatter plot from a single realization from a large matrix. This time n is 16,000. And the black solid line show the theoretical boundary of the complex domain. You also see there are some further real eigenvalues here. Lambda I keep fixed at 1/4, while t runs over time and is indicated here. So let me show you the video. So I will run it twice. So the first time I will stop at some point. So we start when t is slightly slower than 0, and it will decrease. So in the beginning, the complex phase is quite small, while the real eigenvalues are extended. In this plot, you cannot even see all of the real eigenvalues, but when t becomes more negative, the interval with real eigenvalues will shrink. So I will now go to the critical case. So now I just have stopped after the critical case. The critical case is when these two blobs touch at the origin. And now after the critical case, they separate, and the domain of complex eigenvalue will be disconnected. So now the blob will deform again into crescents. And now the crescents are going to touch the real line again. I have now just stopped right at the critical case. So I will run the video once more. So now I want to come back to a few frames which I have extracted from the video. So here on the first frame, t is equal to -1, which is the simple model which I have discussed in details in the previous section. When we modify t slightly, the domain of complex eigenvalues transforms in a continuous way. So for a complex eigenvalue here, there is no continuous way to move to the real axis. For this reason, the fraction of complex eigenvalues at this moment is still the same as here, where it is equal to 2 lambda. While the area of this blob has changed a little bit, the density changes in the opposite way, so that the product of area and density is 2 lambda. Now I want to go further to the critical case. So here we have the critical case when t equals to -3. So in this very moment, the fraction of complex eigenvalue is still 2 lambda. And then in the post-critical case, some of the complex eigenvalues can flow to the real axis. So in this case here, the fraction is strictly smaller than 2 lambda. We also can see that the point where the touching of the two crescents happens is outside of the interval of real eigenvalue density. And because of this gives birth to two new intervals which are disconnected from the central interval on each side. So here we will start to have some new interval of real line density. Here you see the theoretical prediction of the fraction of complex eigenvalue as a function of lambda. So t equal, the green line is t equal -1, which is the one I have shown you in the simple model. You remember this V-shaped graph. But now I'm talking about the complex eigenvalues, so the V-shaped graph becomes this wedge-shaped graph. Now the red line is for t equal -1/3, or it is also for t equal -3, since the model has the symmetry t going to 1/t, while at the same time lambda goes to 1 minus lambda. So you can see that the red line at the beginning follows the straight line, straight green line. Only at some critical lambda, they start to deviate, and the red line is smaller since some of the complex eigenvalues have flown to the real axis. Finally, I want to show you the distribution of the real eigenvalues for this generalized model. So here you see a histogram where we are in the post-critical case. I will now go to zoom in on the next slide in this area here. So here is the red line is the theoretical prediction, and you can see that it goes to 0 here. So that means that this outer interval here is disconnected from the central one by this small gap. You cannot see it that clearly for the blue histograms. This comes from the fact that the boundary effect, so finite size n boundary effects are more pronounced than in the bulk. But you can see that the red line nicely fits with the histogram. We also see that inside of the outer interval, the density vanishes at this point, but here there is no gap, it just vanishes. This actually is the point where the two crescents from the complex phase are touching the real line. Since you are in the post-critical case, we already have some eigenvalues which have flown from the complex domain to the real axis, and all these real eigenvalues you can see in the outer interval come from the complex phase. When we decrease t more and go further away from the critical case, it can happen that this disconnected interval of real density will merge again to a single interval. Let me summarize all the critical cases in this phase diagram. So on the horizontal axis, you have lambda from 0 to 1, while on the vertical axis, you have t. So as mentioned in the beginning, for positive t, the eigenvalues are all real, since then the matrix B is positive. So in this upper half plane here, we do not have complex eigenvalues. And typically the real eigenvalues are on a single interval, but it can happen in this small gray shaded area here that they are appearing on multiple intervals. Let's now go to the more interesting case when t is smaller. So when we have complex eigenvalues. The yellow shaded areas here in this diagram shows the cases when the blobs or the crescents are disconnected. So only in the yellow case, the fraction of complex eigenvalue is given by 2 lambda. Else it would be a more complicated formula. The green line and the red line show the critical cases in the complex domain. So the green line is the case when the 2 blobs kiss at the origin. Since right before these kisses happen, there is already some density of eigenvalues at the origin. The flow from complex eigenvalues to the real line, in this case here, will not give birth to a new interval. On the other hand, for the red critical line, we are in the case when the 2 crescents are touching each other at the real line, and there the interval of real eigenvalues is inside where the touching is happening, and because of that we always have the birth of this connected interval, which is plotted here by this by the gray shaded area. So the gray shaded area is when the real eigenvalue density has 3 disconnected intervals. So finally, we will come to the blue line. This is the critical line when the 3 real intervals merge again to a single interval. When t is negative, it only happens when lambda is between 1/9 and 8/9. In the other cases, it can happen that the boundaries of this interval escape to infinity in such a way that the gap between these connected intervals never closes. Another thing which we can see, that all critical lines, the green one, the red one, and the blue one, intersect at one point, which is the point t equal to -1 and lambda equal to 1/2. This is the reason that when we looked at the simple model with only 1s and -1, we only have seen one critical case, which is the degenerated case, where the upper and lower blob started to deform into a disk. So now I'm at the end of my talk, and I want to thank you for your attention.
So if we can all unmute and thank Roman for a nice talk.
Thank you.
Any questions?
Yes, Roman, thank you.
Anyone has a question? No one has a question?
Roman has been very clear, I think.
Or a comment? Joshua, you have a comment?
I'm waiting to be sure that nobody wants to say anything. And then I like to have the last word.
Okay, I know that.
So
I don't think there's a question, Joshua.
okay. So Roman, thank you very much for your very good talk. I think it was very clear and well presented. I'd like to add a few small remarks, maybe for clarity. First of all, Roman, can you show the slide 23? Yeah. So I want to offer a heuristic, or how do you say, yeah, some heuristic understanding of the forming of these gaps. In general, eigenvalues of matrices either in complex plane or on the real axis can be thought of as point charges in two-dimensional electrostatics, like charges, let's say positive charges, so they always repel. So imagine now that the two crescents that Roman mentioned are now touching the real axis away from the main segment which contains the bulk of real eigenvalues. So there are no eigenvalues on the real axis at the point where the crescents touch. Once they are touching, eigenvalues in the bulk, in the crescent bulk, are repelled from their friends, so that the closest eigenvalue to the touching point are pushed onto the real axis, and that what generates the two little densities to the left of what is it, minus 1.75 to the left, or to its right. Now, when the eigenvalues are pushed from the crescent onto the real axis, some of them move to the right, to the main bulk, where the big density of eigenvalue, real eigenvalues are, and they are repelled. It's like a Coulomb repulsion. It's a logarithmic repulsion. And that's what generates the little gap around 1.5. It's just Coulomb repulsion. And the same thing happens on the other side. So that's one comment, just one heuristic comment I wanted to mention. Another comment, maybe Roman mentioned Ginibre's ensemble. I'm not sure everybody knows what Ginibri. So Ginibri is just a Gaussian, it's like GUE. Roman mentioned GUE, but Ginibri is GUE, but like GUE, but instead of e to the minus trace of a square, you have e to the minus trace of phi dagger phi. So it's a Gaussian model of complex matrices, complex non-Hermitian matrices.
I think we have it somewhere in the beginning. I just not mention it.
Yes, exactly. And one last comment about planar graphs. You described correctly what's going on. I just wanted to mention that when you count the 1/n scaling of each graph, I mean, each Feynman graph has propagators, has vertices, and also has loops. So it's like a loop expansion when you calculate the power of loop expansion parameter, which is h bar usually in quantum field theory. Here h bar plays the role of 1/n, and you can see that the large n scaling of each graph is because it has interpretation of triangulation of a triangulated surface. Each graph scales like n to the power of the Euler character, n to the chi, which is 2 minus 2 times the genus. And therefore, the lowest genus G equals 0 dominates, which are planar graphs. So maybe that. Okay, and here I rest. And I see there is something in the chat. So maybe. Thank you. So again, thank you for your
comments.
Yeah, the question in the chat is, aren't these real eigenvalues called in scattery virtual bound states?
Roman, do you want to take it?
Okay, sorry, I have not acoustically heard the question. Can you repeat it?
Aren't these real eigenvalues called in scattering theory virtual bound states?
I have to admit that I don't know that much about scattering theory that I can answer this question. I'm sorry.
With your permission, Roman.
Yeah.
So if I could think of these matrices as S matrices, then this interpretation might have any meaning, but I don't know how to associate this interpretation with our matrices. Our matrices are indeed inspired by PT symmetry and by the phenomenon of PT symmetry breaking, which is mimicked here by the indefinite metric. But I don't really know how to interpret our non-Hermitian matrix AB or phi as some sort of an S matrix.
Thank you. I think there are no more questions.
Okay.
So let's thank Roman again. Yeah, thank you very much.
Very good. Job well done, Roman.
Thank you.
So thanks, everybody. And we meet again in 2 weeks.
In 2 weeks. Okay. Be well. Take care.
Bye.
Thank
Bye
you.
bye. Bye.
Bye-bye.
Bye-bye.